This conference will now be recorded.
Oh, thanks, Bapi. You missed all of my spiel.
I missed your great
appreciate that.
speech.
Yes. I am grateful.
Sorry.
Thank you.
It was so memorable,
Okay.
it didn't need to be recorded.
Thank you very much. I appreciate that.
Absolutely.
All right, I'm going to go ahead and start. I can't figure out how to turn this into a full slideshow. I think maybe my controls are hidden by GoToMeeting, but okay. So this is my proposal for a design methodology. I have only several slides, so I hope that we can have a discussion about it specifically afterwards. You know, what we're trying to do is create an ecosystem, right? And so to have a great ecosystem, you need to have a solid platform, right, to build it on. And some of the most famous, right, of course, is the iPhone and the App Store. And you know, the iPhone is kind of your closed garden approach, right, or your gated garden where they have to meet a certain level of requirements to get in. A more open platform is the electricity grid, right, which is one of the greatest platforms ever invented, I think even greater than the internet, that enables so much, right? And you literally plug into that ecosystem, right? And you need two connections and you are on the electricity grid and you can do stuff, right? Either take power from it, provide power from it, hopefully someday sell power to it more easily, but it's an amazing platform, right? And still evolving. So, you know, before we define a platform, we just say, what are we trying to enable? So, you know, just want to write this down that we're trying to enable heterogeneous computing devices designed for some kind of application requires a huge amount of number crunching. I'm trying to be as non-specific as possible, AI, whatever, image processing, voice, blah, blah, blah. Want to be very general about that. And then to enable it, what's the main thing that we need? The main building block, I think when we talked earlier, is a processor. So let's enable the processor, but thanks to Alan's presentation last week, I want to broaden that definition of processor, but still use the word processor because it kind of encapsulates, you know, the thing that's the most important, but it could be a big chunk of memory, right? Or it could be a power plant or you know, some big power conversion block somewhere, right? But we have these building blocks that we're going to put together. So each of these processors, quote unquote, needs some kind of services, maybe memory, timing, protection, power, right? So they have these service needs. And then there's the challenges of this platform approach or this heterogeneous approach is that co-design, test, things like thermal derating, you know, because when you put them next to each other, they're suddenly influencing that, right? And I think co-design is one of the hardest ones, right? When you try to get started, you think, well, what do I start with? And then how's that going to affect something? And then you have that circle of design, right? So I want to try to avoid that because we're going to get lost there. And so here's my proposal is that we define things in kind of a processor block. And that block is a processor plus the services that are required. And you give it some kind of standardized dimensions, give good thermal characterization, have standardized behavioral models that can go into the next level simulation, right? And test interfaces for, you know, both early in the process and late in the life cycle, right? So you can see what's going on or what's breaking down. And then we define the platform really carefully, you know, and we can have several platforms based on organic. Instead of debating about whether organic is better than interposer, let's define platforms for both, and let the market sort out which is the one that's going to hit for what applications, right? And we can have all kinds of, you know, standard voltage that you plug into, literally a system monitoring bus, standard test bus or scan chain items. So if the platform can carry a lot of that co-design aspect, then you take the processor, you design its peripheral chiplets that service it and release that as a block that can plug into the platform. So this is the key slide here, and I'll just do one more that's kind of a call to action, is that the most useful thing that we can do as a community is to define a platform or set of platform, and then allow the players or the end users or somebody to spec it in detail and incentivize this design and qualification of the blocks. And then we can really start to experiment with architectures, software, you know, what workloads are going to be enabled or sped up by these heterogeneous devices. But we need to start somewhere, and we need some place for everybody to plug into. So we have an ecosystem. We need a platform that all the ecosystem players can plug into and put their piece of IP. And by putting the services next to the IP, then we can standardize the platform, right? So that's my idea. Thanks for your time, and I'd love to have a discussion about it.
Hey, Ali, this is DJ. I have a few questions. So, thanks for sharing your thoughts with the community. I see two new terms which have emerged, and I think it's very important and crucial for ODSA community to converge on the common, phrases we use. For instance, here you have a term called platform and a term called block. When I look at the drawing on the lower right, I'm not sure if a block is a chiplet by itself, or is it collection of chiplets in a system in package? And then if that's the case, then what exactly is the platform? So, this is maybe slightly a broader question itself, that I think we should all be very uniform in the language we use, so that we can communicate clearly what is system in package, what is collection of system in package on a board, etc. So can you comment on?
Yeah, I did speak very abstractly, and that's on purpose to some extent, because I think as a community we have the opportunity to define what these different levels are, right? And kind of, in a sense, it's levels of abstraction. To me, the block would probably be multi-die, because these things would live in different process technologies, and that's where the co-design is going to happen more so. And then the platform is really about your packaging, your substrate or interposer, or way that you're going to interlink the processors. Because this is about data and crunching numbers, so we want to interlink these number crunchers, with each other so that they can pass data efficiently. So the platform is that pathway, right? As well as things like power distribution and system monitoring or system control.
So, Ali, this is Elko Bergman from ASC. So if I understand correctly, then you're having two levels of heterogeneous integration. The first is the integration of all the processor plus whatever surrounding chiplets. And then the second is the integration of all these various blocks. So it's,
I wouldn't presume that there's an integration step at the block level necessarily, as much as there's a co-design. But then in the actual process of putting it together, it doesn't have to be pre-assembled. They could be still all assembled as separate die.
I thought I heard you say that the block was potentially separate chiplets.
They are potentially separate chiplets, but I don't see, before they go onto the platform, I don't see them have to be pre-assembled together as a block.
So once again, is block a single integrated die? Is that what the block means?
The block is not a single integrated die. It doesn't have to be.
Block is collection of chiplets.
These other services would often be in other process technologies, right?
Right. So block is collection of chiplets.
Correct.
Okay. So I think one of the charter of ODSA, and Bapi can elaborate on this further, is to create a marketplace, and the marketplace, which at least as of now we are envisioning, is for chiplets. So defining chiplets, what kind of chiplets are needed, is probably one of the critical items for ODSA. I think we are going to the next level after that by talking about block, because block is already collection of chiplets in a single package. And then platform is even one level above that, which would be collection of systems in package. Block A, Block B, Block C, D, all of them are system in package. So I think the lowest level would be definition of chiplets which populate the marketplace. Is that how you are imagining, Ali?
I would say that the level of the marketplace is the block. And someone who is interested in selling chiplets needs to define their core processor plus services that are going to plug into the platform. That's why the platform needs to be defined. I also want to go back to one of your earlier, you said the mission of ODSA is to set up a marketplace, but I think that you can't have a marketplace without a market. And right now the market is very difficult because of the complexity of the design. So by defining a platform on which you reduce the design complexity and the co-design complexity, you can open up the possibility of actually having a market that's a third-party type of market that we're imagining.
Actually, platform would be a use case. I think platform is more of an application or a use case. That's how I imagine. So I think probably we should have a separate discussion. Because
so in my opinion, even a block needs a platform, right? So say a block consists of all the little pieces that Ali has on the top right. Even to put that together, you still have to figure out how you're going to assemble it. That itself needs its own platform. Are you going to put them together you're going to put them on a common substrate, but how are you connecting those pieces together? Is it organic? Are you going for something more complex like advanced packaging? So each block.
The platform could carry the interconnect for the block as well, right? The interblock connect, intra-block connect, right? Could be carried by the platform as well.
That is assuming then that your whole platform has the same type of connectivity, I guess.
Hey, we're getting some feedback from someone who's not speaking. So, all right, sorry, go ahead.
So this is Elko again. I mean, so in a way, I mean, when I look at this and I hear what you're saying, Ali, but in a way, what differentiates these blocks from, what are just standard ICs today that are being put together on a PCB, right? I mean, what we're seeing is the standard ICs being disaggregated into chiplets and a core IC. So that's a block. So that represents what, historically might have been an ASIC or an SoC. And then we're combining them on a platform. I think the difference is what you're saying is you don't necessarily need to have the processor and the chiplets integrated into an SIP or something like that before it's attached to the platform. Yes, somebody does have their mic open and is talking in the background.
Yeah, so I don't. Okay, hang on. I think I can see it. Give me one second.
Yeah.
Okay.
To your point, Elko, so for example, if you would have all those blocks on the top right with the same common interface, example, the bow interface. If every one of them had a certain rate of bow interface, then it would be easy to integrate them. And of course, they would have maybe multiple options of die-to-die connection in terms of package level wiring. But it allows people to make chiplets and be able to speak to others than trying to figure out, if you have only PCIe interface, you have only USR interface, you have only HBI interface. But if they do have common, then you and I can all individually go and make our own chiplets and supply it to the ecosystem. And then, yes, the end user who's going to assemble all those in a platform has maybe one or two different options.
Right. So that I totally agree with. I mean, that's really the premise of what ODSA has been working on, right? Is how do we integrate these chiplets with the processor and standardize the interfaces? And I've been a proponent of that as well, because even at the package level, which is where I focus, if we can have standardized interfaces, then a lot of the package level design, whether it's on interposer or organic or through RDL, we can essentially have reference designs already done for those interfaces, which will really speed up the process.
Hey guys, Alan here. I think this is all good conversation, and I think maybe some of my presentation. So what Ali's done a fantastic job of is setting me up with the processor and these pieces, and I think the discussion, hopefully I may be able to add a bit of color to it, may help with this.
So I wanted to make just one quick comment, and Ali, please share your thoughts whether this matches with how you are thinking. So the way I'm looking at this drawing, basically block is nothing but system in package made out of chiplets. I think somebody's feedback is there.
Yeah.
So.
Hang on. Hey, Bill, I think it's you, unfortunately. Apologies.
Hey, DJ, could I jump in here a second? I think what I'm seeing on the screen and what I'm hearing people saying, especially Ali, is that what Ali is proposing is an additional level of hierarchy to simplify the construction of SIPs. The level of hierarchy aggregates into a block, the terminology Ali has chosen to use, multiple chiplets, and then you can come up with uniform shapes for those chiplets that you then coalesce into a SIP. Ali, is that what you're proposing here?
So that is what I'm proposing. You know, and I is intentionally vague a little bit. In my imagination, I don't see a level of packaging, actual physical packaging that happens to the block. The platform will allow the block to be connected with its other block chiplets, but then also provide connections to the rest of the blocks for the data flow. So my idea was by giving the processor its services right next to it and pre-developed and predefined, and pre-designed, then you reduce a lot of that co-design. Now you can really just plop down blocks and decide their signal connectivity, and that way now you can experiment with architectures in a rapid fire. If you have something that works really well and everybody wants to buy, you can always go back and redesign with the centralized power distribution and optimizing for memory and stuff. But this really allows you to experiment with architectures, even with a block that is memory, right? So again, don't say processor has to be a compute object. It could be a storage object. It could be, and maybe it could be an interface object, right? But it allows you to have, place those things arbitrarily and not worry about, how am I gonna, what local memory do I need to do, or how do I protect it, or how do I power it, because it has its own voltages. So then you plug into the grid, right, that the platform provides, and off you go.
So
So,
this
Ali,
is
this is Ravi. Ali, so looks like these are all chiplets, right? Whether we call block A, B, C, D, or even the blue block you have, all of them are chiplets. And we are using green platform as a medium, whether we call it organic substrate, silicon interposer, or any medium, but everything is chiplet on this page. And some aggregation of chiplet is called as block.
Yeah, I had a word aggregation and maybe focus on the word coalescing the chiplets together into sort of a logical arrangement as a block is how I'm kind of assimilating this. I think the real challenge here, though, there needs to be tools, standardized interfaces, et cetera, all the things that we're striving to achieve. And if we advocate this direction from a design perspective, I think the tool chain also needs to catch up to, and the standardized interfaces need to catch up to be able to support it. But I do like it.
Kevin, sorry. Okay, go ahead, Anna. I'm sorry.
No, go ahead, Bapi. You were before me.
Ali, no matter what happens, I think you certainly triggered a storm of conversation. So there's that.
That was my goal.
At least my read of block is the point at which interoperability is required. I think the way I'm seeing what Ali's saying is internal to the block, he's saying you may or may not have interoperability with the open interface we're defining, but coming out of the block, it needs to be interoperable the way ODSA defines it. And that could be...
I think that's great.
Within the block
really
as well,
we summarize it, yeah.
But within the block...
is a good example. I mean, the block with the objects in, you could say HBM is a highly integrated 3D chiplet interfacing to a processor, which is just a monolithic chiplet.
Well, no, our own POC is an example of this kind of design. Each pitchlet in the POC is really a block in Ali's terminology, because each pitchlet has its own, the NIC, the NXP CPU has memory, and the each pitchlet has a set of associated peripherals. But the point of interoperability is what's the I/O to the pitchlet, and what we've always been assuming is that every chiplet has to be interoperable with the ODSA interface. And what Ali's proposing is, well, maybe you have islands which aren't. That's the way I'm reading it. You may or may not agree with it, but I don't think you're saying it has to be multiple chiplets. You're just saying it could be multiple chiplets.
I'm just saying the processor should carry its services with it, so that then you reduce co-design, and then they can all plug into that platform. So if the platform doesn't quite provide the right thing for the processor, then you have some service chiplets in that block.
With the penalty you pay is that you don't have this kind of resource. If each entity has to carry a separate memory interface, it's a valid design, but you're paying a penalty too. I think that's what you're hearing people react to.
Sure, there is a penalty, but the point is to create an ecosystem that can be rapidly plugged into, and that allows for experimental and not just experimental, but a range of architectures, right? Because the key thing is we're trying to enable somebody who wants to use it, and so let's give them options to play with, right?
Yeah, but I think if you redefine block as the interoperability point, it aligns with what we've actually been doing. So Kevin, that's the only thing my read. Sorry, Anu, go ahead. I'm out again.
Yeah, I agree with your clarification there, Bapi. I also like the terminology that you used of islands. All right, so within an island, you don't necessarily need interoperability with the other islands, but island to island is standardized with interoperable interfaces. This is how I'm explaining it.
Ali, do you see this kind of like a top-down approach where you've got platform A, B, C, D, E? Those are the standardized platforms. And if you're building a system, you sort of say, I'm going to go with platform C, and platform C offers me interposer. It offers me these standard data interfaces, and this is how the voltage, the power distribution is going to look like. And therefore, now every block that goes into it has to follow a certain format. Is that kind of the standardized, so sort of a top down?
That's what it is. So that the platform provides you a set of constraints for your block or your island, and then everybody can plug into the platform if they follow the rules.
So Ali, if we have to take a real life example, let's say take an example of AMD EPYC processor. What would you define that as based on this nomenclature?
That's a good question. The services for it are, it's basically, right, there's one interface die, and then there's a bunch of multi-core chiplets around it. And then and then everything else is carried off die, right? So but there may be some power conversion on die, right? But there's no other die there. So it doesn't really match this very well. Like, there's no memory, right? So that's external. Yeah, most of the power plant is external, right? Timing, I don't know, maybe there's some timing shared that the interface does. It's a good question. Maybe that's worth a deeper dive. I'm not an expert, actually. That's why I kind of, this is loosely defined and allows you guys to put some something around it.
DJ, yeah, I think what we should do is we should map this with some real examples, so it becomes very clear to, and that's where maybe we can converge. There are a whole bunch of real world examples from products from NVIDIA to Intel and others, and we can use them as an example to kind of communicate what you're trying to. So you can look at some DGX type of platform and kind of go top down all the way into chiplets and use the same nomenclature, I guess.
I think this is broadening the scope of the ODSA 10 times more, I guess. We have been diligently working on just one of the blocks and just coming up with standards for the sub blocks. And now this opens a can of worm that's going to be really very, very tough to tackle. And it's not going to be done with the 20 people, 30 people job, I guess. As Bobby said, one of the pitchlets is just going to be one block. And that's not going to have all the sub blocks that is listed here.
So I had the same concern, whoever spoke up, which is why I'm trying to see if we can define this very clearly. So far in my mind, I don't have the clarity, but I have the same concern that if we kind of make things a little bit more complex, then it just makes it harder for community to kind of rally around a few focused things to deliver. So, but perhaps this needs to be investigated further.
Wait, before, so if you go back, one of the sort of really interesting things that happened in my mind across our 4 workshops last year, which I really miss, was that at the Intel workshop, at the workshop at IBM, and I forget there's one more place where we sort of coalesced on 2 use cases for chiplets. One is to aggregate a board into a package, and the other is for die disaggregation. Whatever Ali's displaying is a reasonable proxy for package aggregation. It's not a great match for die disaggregation, but it's a reasonable proxy for a reference architecture to aggregate a package into a board. Because you're starting with a bunch of independent.
That's right. And that would be a system design.
That would be a system design. And exactly. So, but I think he's been saying system design from the get-go.
Yeah, but is our charter to go after coming up with standard systems for the industry?
No, but I think all I see Ali advocating is that maybe there's room for interoperable. A block doesn't have to be a chiplet. Really, that's all it is. But otherwise, it's reasonably consistent with everything we're saying. I don't see any advocacy for expanding the scope. I think the only thing I see is, hey, a block needn't be a single chiplet. That's what I'm seeing.
It could be a single chiplet or it could be multiple chiplets.
Could be multiple chiplets, but the block is the point of interoperability.
Actually, the way I see block is a unified functionality. So block A provides a functionality. The way I heard Ali explain, block A, B, C, D can be dropped into the platform by the designer. So block A provides a functionality, block B provides a complete functionality. And that functionality could be as a single chip, which is chiplet, or it could be collection of chiplets, like I guess what the block with processor shows. That's how
exactly. Package aggregation. I mean, I know Brian. I think it was Brian and Jeff or at the IBM workshop that this was one of their leading slides. Was, hey, I'm going to take a package and shrink it into a board and shrink it into a package.
Hey, Bapi?
Yeah.
Sorry to interrupt, but I think this discussion could continue for a long time. Alan has a few slides to present.
Sold.
I mean, the whole point of this for Larry and me was to make this into a bigger conversation. And I think Ali did exactly that. So I think we should keep that on the table to continue, but let Alan proceed now.
Yeah, could I propose we fork off a breakout conversation on Ali's topic maybe next week?
Okay, sure. Oh no, next week is a board review. So, but yeah, we can. But it probably requires some prep. Let's say December.
Let's discuss it at the end of the call. I can prepare or I can share some things, and maybe I can organize that if you want, Bobby. But let's talk about the end of the call.
Yeah. So anyway, the date is December 11th. That's the earliest. So that'll be great.
All yours, Alan.
Okay, can you all see the screen?
Yeah.
Full screen? Okay, thanks, guys. Ali, great start and great debate. I think Ali's covered a lot of areas there, and I'm focusing more on the interfaces side. Obviously, there's a power part, there's a timing, there's ESD. So all of those aspects in these hierarchical things, I think, are very valid. But I'm sort of maybe drilling down into the systems piece, into the actual interfaces themselves. And those of you that saw the memory presentation I did last week, this sort of will expand a little bit on that from a systems perspective. So if I can get my thing to work. All right, here we go. Okay, so I'm focused on the one primary processor chiplet interface, and we've got lots of different interfaces, but this has been where I've been coming from a memory-centric perspective. In memory and I/O, at the end of the day, distant memory is really I/O attached, so they're one and the same in my mind. So we want the highest terabits per second per millimeter, and I was trying to help to focus on why that is, with the lowest possible latency for those coherent, tightly coupled memories to the von Neumann engines often used, lowest power, lowest cost and scalable, and importantly, accessible to the whole industry. We want tier 2 and tier 3 players to be able to leverage this, not just the tier 1 guys. So that's the sort of a requirement. So if we really put the focus on the interface, and we did only have one rather than a multitude of them, then again, the classic ratio is it flops bytes per second in bytes of depth for when you interface to this tiered memory and I/O infrastructure. So our history is really giving us this. At the flops end, we've focused greatly on massively increasing the flops over the last 30 years in memory depth and things like NAND and other things. We're now getting much deeper memory. But the bytes per second, i.e. getting data in and out of the processor, has been a sad reflection on focus, and as a result, we've got all these caching hierarchies to get over this von Neumann bottleneck. So I think the focus that we need to have in the ODSA is really we need to put the bytes per second in the middle of our focus right now to go forward, and that's I/O and memory. And this is where my head is driving from on this. We've already done it with HBM, but HBM has done a fantastic job of expanding that bytes per second, but at the same time, it's dramatically shrunk the amount of memory depth. So we haven't got, the proposal is, can we have HBM and also have that memory depth option? So that hopefully that emphasized my focus here. So this is a slide I presented last week. It's just showing the memory as a centric and all the memory options as we go more data centric, and the processors are on the periphery, right? So we want all processors to have this same interface. But when you look at it at the HBM, I emphasized here this interchangeable between HBM and I/O. So what I've done, if we are going to standardize on one interface, this is the chart that you guys have all pulled together with all the various standards. And I've taken, out of my requirements, I've taken what I think are the most important factors. And by the way, this isn't a definitive answer, it's just my perspective on it. So you can look at the details. I've got green, amber, and red is whether they're great, poor, or okay. And so when I score higher is better, 0 is red and 2 is green, we see the interestingly, the ultra short reach NRZ from AnalogX seems to be the winner, just adding up the numbers, and I've got no scaling. So again, take this with a pinch of salt, but I did this analysis and I picked this interface is giving us the best balance of power, speed, density, etc. So happy to debate this. And so I'm going to use, because the USR-NRZ wins, I'm just going to use the terabits per second per millimeter as my point for going forward. So theoretical bandwidths that we could potentially achieve per processor with this USR-NRZ. If we had an NVIDIA Ampere die, the massive die that I think is the biggest anyone's ever built and probably ever will build monolithically, we see that with that I/O, this is all theoretical, right? You use every millimeter for the I/O. We could get 253 terabits per second, or 31.6 terabytes per second, compared to the NVIDIA Ampere at the moment. It's got 1.5 terabytes per second. So interestingly, this interface is absolutely more than enough, looking at it from a big die perspective. But it's equally at 0.9 picojoules per bit. And that speed, we're looking at 228 watts just for that I/O, even though it's the ultra short reach. And the number of bumps is just a number of bumps. But we know that the NVIDIA Ampere has 30 single precision teraflops. So now we've got a one-to-one with this theoretical concept of 30 teraflops to 30 terabytes per second. We've suddenly given the focus back to a one-to-one ratio there, which is fantastic news for certain applications. But as the die size goes down, interestingly, the I/O bandwidth goes up relative to the flops. So in one example I gave last week, I had an application that only used 1/30th, one single precision teraflop of the GPU for the 1.5 terabytes I/O bandwidth. So with this, we can see, interestingly, with a smaller die, by focusing on terabits per second, we can actually get 5 terabytes per second into this die. And for a one single precision teraflop. So suddenly we've actually improved the bandwidth to the flops, sorry, which is great. And so it gives us these other ratios that I was talking about last week. And me as a processor company, I can design a little processor or I can design a huge processor. They've all got the same interface. So basically I can connect anything, I/O, memory, whatever I like, HBM or distant memory over I/O. So if we look at a footprint compatible memory I/O chips, if we can get there, we could add a graceful addition of latency and power as needed for our application. So let's take this package module again with the HBM. So we're looking at that. If we changed the HBM interface to be USR-NRZ, and we added this OMI layer, which is a memory interface over transceivers, but with this low power transceiver I/O, we could get a very low power HBM, still just the same, maybe a little bit more power than the current HBM interface, but we could still deliver the same performance. But if that HBM was then interchangeable to an electrical buffer or a photonic buffer, then we could get I/O out of this when we didn't want memory for our application. Taking the electrical buffer, if we wanted to connect to local memory like memory DIMMs to get more depth, which HBM can't give us, we could simply then put an OMI retimer that would allow us to actually reach that DIMM in a minimum of latency. But obviously this retimer would absolutely be latency critical. So I've said here we'd need to target less than 500 picoseconds for this buffer. But equally, when we wanted to connect other interfaces like CXL, Ethernet, Gen Z, PCI, C6, we can then build bridges as chiplets to bridge out to those other standards which may be more appropriate for certain applications. And so, but that's when we're more latency relaxed, and what I mean by that is greater than 500 picoseconds of latency. So we've not given up the local memory on the system when we don't want HBM, but we want more deep memory. And when we want to get more sophisticated and elaborate with these different interfaces or backwards compatibility, we can do it with relatively low cost chiplets. So if we go with that approach and then we look at the memory end of the stick rather than the processor end, various memory focused chiplets can provide us with depth in bandwidth scalability. So we've got on-package memory chiplet examples and off-package memory chiplet examples. Well, obviously the on-package memory chiplet example is HBM. We know it's split down into DRAM stack plus logic base die. And we have to upgrade that logic base die to USR-NRZ. But so it would look something like this. We would have our USR-NRZ PHY with our OMI translation and the memory controllers. And we could optionally put a processor near the memory. And so that would really keep our power down massively if we had small processor functions to work locally on the memory, and we don't want to burn the power of the communication. So this is an important aspect of distributed computing. So you can trade communication with central processing or distributed processing. Likewise, with this type of interface, unlike the current HBM interface, we could interface to a NAND stack or a 3DX point stack or an MRAM stack. And obviously the logic die would have to change. So obviously this is going to be 3D TSV type integration, which the big guys are really focused on. I think in Ali's block, these would be various blocks with a really expensive die stacking capability of the big guys, but they're in a granular element that a tier 2 and tier 3 can utilize. There's no way a tier 2 or tier 3 would ever create these, but they could utilize them. So I like the hierarchy that Ali's showing. From an off-package perspective, we would have the chiplet buffer converting us back to USR from our CXL or our OMI or whatever. And then we'd have our local memory buffer that talks to the memory standard, the media that it needs to talk to, which would be multiple package memories, like a differential DIMM. So I've shown 3DS DDR4, so a standard DDR4 DIMM channel this would be. And the memory buffer would collect those up and then transport them over this common bus. Again, the memory buffer would look pretty much damn the same as the HBM logic die, but obviously with different memory controllers on it. So that's the only difference there. And again, we can change those memories from DDR4 to LPDDR4. It's got some very nice characteristics in terms of speed and low power. We could put 3DS NAND, 3DS X-Point, or interestingly, we could even put HBM. Imagine putting 8 HBMs to a tiny memory buffer die, and then you would have some local processing, but you would be able to shrink down to maybe a smaller interface and have many of those HBMs. So you then have what you would call a scale up sort of thing with the big processor piece and a scale out. So things like map reduce type functions, the mapping functions could go in the local processors with a really fast memory, and the reduce functions would go in the big die. And so this is quite a small subset of parts we're talking here. And basically that's my presentation. So it's trying to, so I think that the question was, what are the chiplets we want to build? And I think this could, I've started to define a base level of chiplets here that we could work with. And that's my presentation. Thank you. Any questions?
Great presentation.
So Alan, this is Suresh. Are you arguing for standardized footprints where the functionality could be different, but the footprints are standardized and you could mix and match them in a system?
Yeah, so this HBM interface, let's just say we have an HBM interface. I mean, arguably it could stay HBM, and then we just have the buffers going to HBM, but that forces us into a silicon substrate. Whereas I think the USR-NRZ, if you look at my metrics, organic was one of my metrics, and for tier 2s and tier 3s, I think we need some level of organic. We can't afford, the industry is going to be down to 2 or 3 players, so what's the point in having a standard, is my view there. So yeah, we'll have an HBM footprint with a USR-NRZ interface on it instead of standard HBM, and then we would be able to swap that out for an electrical buffer or buffers or a photonic buffer, depending on the I/O we wanted, and then we would have a whole family of electrical buffers depending on which standard was your favorite standard to support, CXL, Ethernet, PCI, Gen Z. But we'd also have the really low latency one, the OMI, the native memory one, that would allow us to get low latency to external deep DRAM as well, as that. So that's the idea. But yes, they would be a standard footprint, or some sort of, maybe you could put multiple smaller dies on the same footprint as the HBM die, depending on the channel breakup. I think HBM is 8 channels, so maybe you could put 8 individual buffer chips on the same footprint as one HBM. So it can be sliced a lot of ways. Obviously, that's part of the challenge, is how you define a footprint that can support all these scenarios.
Alan, the HBM today is a parallel interface, right? So you have here the HBM talking to your processor using a USR-NRZ. So we're talking about a different kind of PHY to because
Yes.
the standard HBM PHY today is not going to work for this.
Yeah, no, that would need the HBM guys to buy into this, or alternative, we say the HBM guys are right and we all adapt to their interface. I mean, that's another option. It just means that forces us into silicon substrate. So that was why I did the comparison. I think we're a standards body for the masses. We're not a standard body for the big guys, because the big guys would just do their proprietary stuff. So there's no point in us doing a standard for the big guys. But so that's why I weighed all the, this is where this chart really comes into the fore here, is it's all about, so if you look, this, because it won, if you look at the USR one, it's 2.199 terabits per second per millimeter. I think, I'm not sure where HBM2 plays, whether that's OpenHBI Rev 2 or something different. HBM3 has a lack of information, so I don't know, but I'm assuming we're at 2.86 per millimeter. But we can see that the power is really good, it's only 0.5, whereas the USR is 0.9. So that's a penalty of USR as the extra power, as I've shown. But the latency, good.
Yeah, what I like about this is, I mean, you are narrowing the focus.
Yes,
I mean, focusing on more of the interface between the memory and the processor specifically. And ODSA right now is chartered to do, a little bit more. And the other option presented earlier is much bigger scope. So, yeah.
Well, I'd say memory and I/O, because all I'm saying, what my previous presentations I've done in the past is saying that memory and I/O are basically one and the same today, because we treat every, if you look at all these memory fabrics that are being talked about, essentially they're I/O to distant memory. And local memory is only HBM is local memory now, and even a DDR4 DIMM is distant in terms of our world of chiplets. So therefore, it becomes I/O.
Excuse me, Reza. So go ahead. You can please finish.
No, that's it. That's fine.
So, excuse me, Reza. I want to push back on the concept or the idea that my proposal is broadening the scope. I would say that what it does is it narrows the scope for individual actors. So if we look at someone who's providing a die into this ecosystem, they're going to say, well, how is it going to connect everything else? Now they know, or they know they need to add certain things to make it compatible if we can define a platform. So it really, I think it actually narrows the constraints and gives freedom so people can do something. I feel like right now we talk a lot, but we're not getting the point of anything actionable in terms of actually, putting together the full system, right? I mean, say, how are we going to do the test, and how are we going to do this, and how are we going to do that? But we haven't, again, put something together that's actionable, and that's a proposal that moves us in a direction where by defining something, then you can take action on the individual parts, and it deals with a lot of the co-design issues too.
Yeah, to be honest, I mean, when I looked at it, it just, to me, it seems like it's similar scope as the OCP rather than the ODSA. The OCP is trying to come up with some standard ways of interfaces between the systems for the system level. I may be wrong then.
Hey guys, Reza, I apologize for breaking in. Anu, we're at 8:57. Is there anybody else, or do we redo? How do you want to handle this?
So I don't know if there was anyone else. There was a couple of guys who said they would talk, but I didn't hear back from them. There was Swami, Vikrant, and Gus. And anyway, we've run out of time. I believe this has to probably be extended to a second discussion, Bapi.
Yeah. So okay.
Yes, I agree. I think.
So Bapi, this is Swami. Anu, yeah, I do have a few slides to share. Maybe next time.
Okay. So why don't I do this then? Okay. So then in that case, I'll see if we can move the board discussion back. And should we just continue this next week as a group? Where anybody want to weigh in? We were originally scheduled to do Bo, but we can push Bo back by a week.
I think that's a good idea, but I have a suggestion, quick suggestion for that next discussion. can we take examples like the Zen Epic, or as Dharmesh was suggesting at the beginning, there are 2 or 3 existing models that are working for different companies, and democratizing that for the rest of us would be a
Suresh, I'm sorry, breaking and interrupting because we're almost out of time. Look, if we want more work from the presenters, then next week is hard. In that case, a better option is to sort of schedule this for December 11th. If we just want to continue the discussion with whatever material we have, the next week is the option. So what's the combined wisdom of the crowd here?
I think we let people mull over it a little bit, and so to push it out.
Anybody else want to speak up one way or the other?
I agree. Let's push it out.
Okay. Anybody opposed to pushing it out? Other than the people who worked hard to make decks with this. Any objections? So go ahead,
Very
please.
nice discussion. I think we can push it out. Yeah, definitely. I think we have,
okay.
Based on today's discussion, we can expand it to even further, including some test methodology as well. So thank you, Anu, and this is nice. Yeah.
Swami, would you mind? Sorry, Anu, I just want to nail this down. I apologize. Swami, it's okay with you if we do this December 11th?
Absolutely. In fact, I was going to say, Bapi, Ravi has arranged for the panel discussion where we're going to be presenting a lot of our stuff. So I think by December 11th, we should have more inputs towards this. And
Awesome.
I think the platform that Ali provided today is excellent for us to talk about.
Could we make it a panel discussion at the Tech Week? Is it worth it, or are we too unfocused right now?
No, that ship has sailed, man. Somebody will take my head on a platter if I propose any changes. Yeah. So in that case, Anu and Rita and Lei, Anu, many thanks for this. It was a very nice discussion. Ali, thank you. Alan, thank you.
Hey, thanks to Alan and Ali. I appreciate the help, and Rita and Lei. Thanks.
Yes. Thank you, everybody. That was great.
And the one thing I have is a request that, next time, maybe by December, we settle on a common terminology. That's the one ask, what we mean by module block, and maybe we can hit that before the 11th. So that when all of us use roughly the same terms and that we don't overload existing industry terms.
So, Bapi.
And Bapi, go ahead, Ramesh, go ahead.
Yeah, just final comment. I think what we'll do is business work stream will take the ownership of coming up with the common terminology. So we'll provide that to the community. I think it's a great idea. We need to have a common nomenclature, and we'll explore what is being used in the industry and work together with everyone.
Okay, Anu, your whole single slide thing really set it off. So well done. Thank you, Anu.
That's all I need. One slide, and then I'm all set. Thank you.
Thanks, everyone. This is a very engaging discussion. Have a good weekend and everything.
Bye.
Bye.
Thanks, Bapi.
Thanks, Bapi. Bye.
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 Thank you, Bye.